Hello and welcome. At the risk of being repetitive and trying to speak to the choir, I guess all of you by now know about lean manufacturing and have maybe transitioned to lean service, lean hospital. I felt that before you launch into the lectures on job shop lean, starting with the next lecture, that I should maybe go over the fundamentals of lean manufacturing, and then from there give a transition into why job shop lean and the specifics of job shop lean. So if you notice in this title, I have used industrial engineering based on the Toyota production system. I did not get onto the lean bandwagon. In fact, I distinctly remember as a graduate student that I saw these papers on just-in-time and Toyota production system appearing in the IE magazine, and I just at that time kept saying, that's for the assembly line. My industrial engineering is more about cellular manufacturing and high mix, low volume. I was very wrong, and today I believe that the Toyota production system, even though it has been recast by American experts as lean and Six Sigma and what have you, that this production system actually inspires a complete rethink of the industrial engineering curriculum that we would teach. And really, job shop lean is just me as an industrial engineer with a background in operations research and some computer science, figuring out, hey, these tools that people use to implement lean, these manual tools that Toyota has pioneered, actually there's a way to implement them on the computer, especially because in high mix, low volume, non-assembly environments, many of the problems are so large, the analyses are so difficult that you could not do them by hand. So let us basically continue with the overview of lean manufacturing. So here's one definition, and I'm sure there are many definitions. What is lean manufacturing? If we understand that competition is really about speed, getting the customer exactly the product that they wanted in the right quantity with unquestionable quality, but quickly before the competitor can do so, that's this whole concept of lead time. So one definition of lean manufacturing is a philosophy. It's this thinking process that we wish to shorten the total time that the customer has to wait. So essentially it would be administrative lead time, the time it takes to accept the order, to process the order, to make it ready, get the go-ahead from the customer, and then once you release it into production and manufacturing, the production lead time. Of course, if you wish to do so, you can even add distribution lead time, the time it takes to get the product after it is on your shipping dock to the customer. So lean manufacturing is a manufacturing philosophy that shortens the customer wait time between the receipt of a customer order and the shipment of that order to the customer by eliminating waste. So fundamentally, and there's a bias, I'm kind of also influenced by theory of constraints and constant work in process, quick response manufacturing. If we're looking at shortening the total time that the customer has to wait, essentially what lean embodies and what Toyota really opened everybody's eyes to is a lot of the time that the order waits, not being completed, is in waste. And so effectively, waste may be about materials, may be about labor, it may be about energy, electricity, but I think what you have to say is waste eventually translates to a time delay. And all these delays, when they add up, they essentially increase the total customer wait time. So what lean essentially says is, if you systematically attack the waste, you eliminate the waste in one way or the other, you are shortening the total customer wait time. And so that's this thing that I kind of added to the original definition. Anytime that an order is delayed, the cost of one or more of the 7 forms of waste gets added to the cost of producing the order. And then besides cost, of course, you have time. So many times people say time is money. Well, when you increase the time it takes you to ship an order, you essentially are costing more and you are paying yourself less, unless of course you gouge the customer by raising the price, which is not good business philosophy. So lean manufacturing essentially shrinks the total time it takes by eliminating the delays caused by waste. What are these 7 forms of waste? Once again, I think it is Ono, it is Shingo, Kobayashi, all these Japanese experts who took the very narrow definition that industrial engineering had of waste, which was mainly about motion, motion economy, what the Gilberts did. Maybe it was Taylor who talked about, waste too, but I think it is people like Shigeo Shingo and Taiichi Ono and other Japanese experts such as Kobayashi who fundamentally said that there are 7 forms of waste, and that if you target these 7 forms of waste, there's a good chance that you will also reduce the total time it takes you and the cost of fulfilling an order. So the first waste, of course, is correction. Scrap, rework, easily. You have to repeat work you already did, so you're essentially adding the delay and the cost once more to the cost of the product, to the time it takes you to complete the product. Then labor, everybody is very sensitive about labor. And since people spend their time walking around in motion, time it takes to go to the tool crib, get the tools. Time it takes to seek your supervisor, clarify some paperwork or get the paperwork and then come back to your place of work. Time it takes to just stand around waiting for the machine to finish its cut. That's a form of waste. So the second form of waste is just motion of any kind, involving people usually, but sometimes even on equipment. When, say, a machine tool, the tool is basically traversing between locations, it is not cutting. When it's not cutting, it is not adding value. A subtle form of waste is overproduction. Many companies say we have on-time delivery, 100% on-time delivery, and when you press them, they say, well, we basically fulfill from warehouse inventory. Well, that's of course quick response, but the question is, why did you have so much in inventory? And how often do you, at the end of the year, write off obsolete inventory? So many times we overproduce. Why? Because if we chose to produce an order from scratch, then the overall lead time, the total time it would take us, the customer wait time, would far exceed how much time the customer would allow us to fulfill the order. So therefore, overproduction is any time when you produce a product, but you do not ship it, you store it with the expectation that it will get sold. So for example, material requirements planning. The fundamental logic of MRP is you forecast demand. You forecast demand, and against that forecasted demand, you schedule production. Well, we all know that forecasts are not as good as actual committed orders. So overproduction is another form of waste. Transportation of any kind. When you use equipment like motorized conveyors or forklift trucks or cranes, not only is there the labor cost, the equipment cost, the depreciation cost of the moving done by the equipment, but then there's a delay involved if the equipment is not available or the operator that was required to operate the equipment was not available or the equipment broke down, right? So that's the fourth form of waste. Again, that contributes to cost, delay. In many cases, material handling damages the product. So conveyance waste could even add to quality waste. Then of course there's the classic inventory. Raw material inventory, finished goods inventory, which of course is here. But then the easiest opportunity in terms of inventory waste is work in process. And therefore, Kanban lot sizes, the buffer inventory that theory of constraints promotes. These are examples of controlled amounts of inventory, and that as long as you have that much inventory in the system, you do not produce more work in process. So this inventory really is about work in process. One work center can produce faster than the work center which will receive its work, so it just keeps on producing. In effect, what happens is its output goes into queue at the receiving work center, which is slower, and therefore you have a work in process waste. And of course, the work in process waste often relates to the waiting waste. Any time that orders wait in queue because the machine's broken down or there are other orders in front of it, it's costs. It's basically the carrying cost of inventory. So queuing waste, waiting waste is the sixth form of waste. And of course, a very subtle but often forgotten waste is processing. See, we industrial engineers, we tend to break up any work process into some classical elements. The elements would be operation, transport, inspection, waiting, and then delay of any form. We tend to think that every operation is value adding. But many times the question is, are you using too many operations? In which case some operations are waste. Then are certain operations very time consuming? Are certain operations causing excessive tool breakage or material spoilage? So many times what we think is a value adding step, processing, is actually potentially non-value adding. So these are the 7 forms of waste, and I think again, as an industrial engineer, I can tell you how eye-opening and refreshing it was to realize, you know what, it makes sense. You go into any workplace, any office, any hospital, any manufacturing facility, any warehouse, and you start seeing, wow, these 7 forms of waste truly do exist. The challenge, of course, is to quantify the value of that waste, and then to inculcate in the people doing the work what they thought was actually work is actually wasteful, and that if they redid how they do the work today, that the company would benefit and they would benefit. So often we think we know the work we do, but when somebody else from outside comes in and maps our work and then points to and questions us about certain steps and says, do you know these steps are essentially one of the 7 forms of waste, it takes some time to kind of accept that humbling discovery and say, yes, that's correct. But I think, again, as an industrial engineer, or even as any industrial engineer, the 7 forms of waste are what truly add to the cost and delays in fulfilling an order. Now, this book is of course a classic, the book by Womack and Jones. I would highly and strongly recommend that all of you read the book. I'm sure you already have. They have another good book, Lean Solutions. And of late, there's a book published by CRC Press written by this professor at Loyola University in Chicago, John Nicholas, Lean Production. At least as an academic, I find this book extremely refreshing. At least he takes an academic, a scientific approach to lean production. So, again, these would be a couple of very good books. The book by Yasuhiro Monden, Toyota Production System, that's a little more technical. Another very good book is Taiichi Ohno's own book on Toyota Production System, and of course Shigeo Shingo's book on Toyota Production System from an industrial engineering viewpoint. Anyway, Womack and Jones, again, something extremely significant that they did, again this is a personal opinion, is they took process improvement, they took production systems design and broke it up into this 5-step process. And they said, when you undertake to implement lean, be it in a hospital, in your backyard, inside your refrigerator, in a warehouse, in just about any manufacturing facility, pursue it in a 5-step process. And so the first phase, of course, is define value. And again, the value should be defined from the viewpoint of the customer, not you, the producer and supplier, from the customer. It makes a big difference. The second step is, of course, having defined value, you identify what are called value streams. So in most manufacturing contexts, a value stream is easily either a product, a family of similar products, or a family of components that get used in multiple products. These are typical examples of value streams. A sequence of steps and activities that essentially deliver something of value to the customer. That is the second step. Having identified the second step, you undertake to do layout changes, material handling changes, you institute visual control, you look at poker yoke, you look at water striders. Essentially, you look at the layout design, everything that has to do with the physical flow of the product. Try to eliminate all wastes and delays in the physical flow of product inside the value stream. That is step number 3. After you have eliminated the flow related problems inside the value stream, then you institute pull production. You only produce to demand, and you check very carefully that you are not overproducing certain products, and you try to share your capacity, especially on the bottlenecks across multiple products, by reducing changeover times. And so there are methods like Hijinka, constant working process, or convict. The idea again is that you institute pull manufacturing, you produce to the demand of the market, but only after you've improved the layout. Now once basic layout and scheduling are instituted, then you essentially institute continuous improvement as an ongoing logic inside the value stream, and you pursue perfection. So this would be, people go back, they again look at what can I do, where is the bottleneck step inside the value stream, and they keep pursuing this. Now, once this particular value stream has been improved, then you switch to the next value stream. And so it's a very eye-opening, a very systematic process that I think lean thinkers essentially pioneered. So let's discuss now the various phases of this process. So of course, the first step, define value. So what is important is that you try to quantify the metrics which you're using. Don't have too many metrics, but of course quality leads off. You do not want to ship a bad product, a product that quickly fails in the field. You wish to fulfill delivery, and of course you wish to be cost competitive. So quality, cost, delivery, these are typically standard accepted measures of value. The big question is, can you do better than your nearest competitor? And can you supremely satisfy the customer where they say, my God, I mean, you quoted me a price, you quoted me a due date, and you more than fulfilled my expectations. The second thing is, again, something which many of us forget, many companies forget is, once you define the customer metrics based on delivery, quality, cost, only then do you define in-house metrics. And these in-house metrics should be defined in such a way that they directly help people to understand the work that they're doing. And so when they draw the process maps, they do their process control sheets, they create their value streams maps. Those metrics that they're using inside those value streams directly help them to identify, measure, and eliminate the waste, no matter in which level of the company the employees or managers are working. And so I think the important thing again is that many companies tend to look at, say, utilization as a metric that if they institute inside the company, automatically guarantees that they will fulfill the customer expectations of delivery, quality, and cost. Wrong. I mean, theory of constraints easily tells us that if you have high utilization on all non-constrained work centers, you've pretty much wasted your resources. If people have to pay overtime to get work done, and essentially the work that gets done goes into a warehouse, how does it help them to get the work done? So it's important but often challenging for the typical manufacturer, especially the small manufacturer, to kind of get out of that mindset that things like buying more equipment and buying flexible automation and paying overtime is good. Many times those in-house metrics are actually running counter to the philosophy of lean, which is deliver on time, good quality at competitive cost without it costing you too much to do that as the customer wants. So this came out of the Lean Thinking book, and it's so fundamentally valuable. Waste is basically anything which you do that you would call as non-value. So what's non-value? Anything that, in the eyes of the customer, adds cost to the product ad or the order that they have asked for, without giving any functionality or value to that order. So, in many cases, getting to understand or view what you do from the eyes of the customer, how can you criticize your own work? How can you criticize your own product? Sometimes, you have to do that soul searching, and that's where you discover waste. Okay? So waste becomes anything that would not be valued by the customer. So again, just a quick repetition, these are the 7 forms of waste. Quality and rework. Why would the customer want to open the box and find a broken thermometer? Why would the customer want to open the box and find that his bicycle or her bicycle has only one wheel, that the second wheel was not shipped? Why would you want the customer to pay? Of course, if the customer doesn't know, they would pay, but why would you say that, well, part of this price I'm charging the customer, 2% of that is coming from my people walking around looking for tools. So the 7 forms of waste, essentially they're non-value added. So if you identify those wastes, you are essentially helping to eliminate what the customer would not want to pay for. Please look at all these action words. How do these non-value added activities impact delivery, quality and cost. Think about it. None of them really contribute to delivery, quality, and cost. If you take a hard look at it, and if you ask all your employees to describe the work that they do, and then once they wrote up their statement in an email or a Word document, go and check all the action words, the verbs as we call them. When they spend time counting, or they're sorting, or they're printing out or typing up acknowledgements, when they're printing out invoices, filling up invoices. In so many cases you would think, hey, we have an ERP system, an enterprise resource planning system in-house. Why couldn't that system help to automate some of this document preparation effort? Why? Why would you say, well, I reworked the part? It's not value adding. So many times if you just ask people to describe the work they do, recorded that work, and then sat down and highlighted all the action words. When you start seeing words like these showing up in that work statement, you quickly start being able to say, what? All of these actions you're performing, please look at it. They really do not add value in the eyes of the customer. So like this, I would challenge you, do a small assignment. Write down in your own words what you do, or what you think is the description of your work during the day. Then sit down, check the action words, see how many of these non-value adding activities you're actually performing in the name of work. Either because you didn't know about it, you didn't care about it, or you didn't have a chance to really criticize your own work. Second step in lean thinking, value stream analysis. So again, we will discuss this later, but most of the time in job shop environments, you can't just pick up one product's assembly routing. You have to look at the products from a volume perspective, the routing, bill of material perspective, the value. But again, the point again is define a value stream. Value stream are all the activities, all the supplier responsibilities that go into fulfilling a product or a service. Okay. Now, once you have the map, you essentially go and assess the value-adding contribution of each step. There's a whole book, Learning to See, on value stream mapping. I do not wish to bore you with those details. But the point again is that the value stream is all the steps, the material processing steps and the information support and other services that go into supporting the execution of the value stream activities. Then once you've analyzed the value stream, what you wish to do is you either eliminate all non-value adding steps, so things like delays due to equipment breakdowns, stoppages due to absence of materials, high variability in the cycle times or changeover times at bottleneck work centers. These are all the opportunities, and value stream mapping is such a powerful method. It helps you to quickly, using a combination of maps and numbers, zoom in on where you should be focusing your efforts to eliminate non-value adding steps. And of course then you try to see what will be the true impact on quality, cost and delivery by changing the value stream, and it's often done through small steps, but a series of small steps continuously implemented, always to keep improving the value stream. That's the second step essentially. Identify the value stream, do the documentation analysis, and then identify what improvements you should make, always starting by saying, first and foremost, let us eliminate all the non-value adding wasteful steps in the value stream. The third step, of course, is flow. You try to flow product. So, of course, ideally you would like to flow product through the supply chain, manufacturing and distribution portions of the value stream. Now, that's being utopian. I think that the supply chain and the distribution chain, unfortunately, given that large distances separate the manufacturing facility and the warehouse or the supply facilities, there is going to be inventory. There is going to be inventory in those portions of the value stream. But really, inside the facility, you do wish to reduce the total time it takes. And what I've shown here are the classic inventory triangles. So what you're trying to do here is, imagine, if this is time, if this axis is time, and this axis represents inventory, then what this line represents is that the more that you produce at a particular work center, and what you produce is not removed from that work center and taken to the next work center, more and more the inventory increases. So what just-in-time and one-piece flow ideally would want to achieve is you produce so much after so much time, and then immediately it's taken away to the next work center or it's shipped to the customer. After so much time, once again you produce so much of the product, once again it's not allowed to accumulate, it's shipped. So eventually you do end up producing this inventory, but at any given time this is the maximum inventory you keep. And there's a simple rule that when the travel distance between consecutive value adding steps is minimized to the extent that they are brought next to each other, you have essentially one piece flow. So you're able to flow product through the value stream by significantly changing the layout. And therefore, what Toyota has been able to do is, because of the high volume of their products, they're able to create assembly cells. And so assembly lines are a natural for achieving flow. So once again, to get flow, what you try and do is you make each product in direct proportion to demand. Okay, so if you make products A, B, and C, the best way to minimize the growth of excessive inventory is to produce these different products in proportion to their actual demand. And then by minimizing setup, you're able to have repeating sequences of production. So at the end of the day, of course, you produce the desired quantity of each product, but at any given time, you are distributing the inventory across all the products in the mix. So again, this process of Haijunka or mixed model production is generally relevant in low variety, high volume environments, which is assembly, where Toyota operates. On the other hand, if you're a job shop and your value stream is actually a small job shop in its own rights, then I think what you want to do is something called finite capacity scheduling. And what finite capacity scheduling does is, even if you're a high variety, low volume cell or a facility, the scheduling software automatically picks up where the capacity constraints are, the bottlenecks, and then you will not see the system releasing those orders into the shop where those orders would end up in queue at the bottleneck. So I think that please understand that when you achieve flow and you're trying to make each product each day, but in a job shop, what you're really doing is you're accepting due dates on various orders, each with different quantities, and then you are scheduling the production of these orders subject to the available capacity on one or more bottlenecks in the facility. So there's a slight difference between these two. When you achieve flow in a facility, it's different when you have a low variety, high volume facility, and as opposed to a high variety, low volume facility. But once again, that's the goal of flow. Try to compact the facility, minimize travel distances, put consecutive work centers close to each other. Why? Because the shorter the distances, the more that you will be able to achieve the ideal inventory situation, which is one piece flow. One work center makes a unit of product and immediately passes it on to the next work center, else that unit goes into queue at the next work center, and that queue blocks the supplying work center from producing another unit till that unit in the queue was consumed. Fourth one is, of course, just-in-time pull scheduling. You're always trying to, what essentially pull scheduling is saying is, ship something because it was demanded by the customer. Now, check that something which you shipped, is there another demand for that same item which you shipped? Yes, there is. Go ahead, initiate production. So the idea again is that you are pulling from shipping into receiving because shipping is nearest the market. So that is market pull. And so what JIT, just-in-time pull scheduling, is saying is, inside the value stream, when you look at what's shipping, sent to the customer, against that a demand for that particular product, now you initiate production in assembly. Assembly will initiate production in welding. Welding will initiate production in fabrication. Fabrication will initiate supply by the suppliers. So it's kind of reverse compared to push scheduling, which is you forecast the demand and just start producing products, even though when they get completed, there is no guarantee that there's an actual demand for those products. So some of the features of pull scheduling are, you authorize production to replenish only shipped quantities. Again, please be careful. It's okay in the OEM high volume assembly environment, when you ship 20 units of a certain item, there's probably a very high probability that that same item will be in demand, so you are justified to make another 20 units. That may not very well apply in high mix, low volume job shops. Another strategy or requirement is you limit the work in process that is allowed at each step. So Kanban lot sizes are one way. You're holding work in process in front of each and every work center in the value stream. Theory of constraints drum buffer rope says hold a certain amount of inventory at a particular work center, the bottleneck in the value stream, and then control how much you release into the system. Meaning, if you don't process raw material, there will be no work in process. A third expectation is to stabilize demand. This is again trying to control the market, trying to get the customer to accept delivery dates and delivery quantities that would allow you to have like a balanced assembly production inside the manufacturing facility. And of course, what theory of constraints and constant work in process embody is, if you don't release raw material into the system, you will not have work in process. So if you release raw material, it's with the confidence that you will be able to complete it and ship it to the customer. On the other hand, if you have to have work in process, hold measured amounts of it at the bottleneck work centers, and then let the other non-constrained work centers only work for the amount of time required to keep that buffer, that bottleneck, full. Otherwise, let them remain idle. So there's some very, very powerful concepts of pull scheduling that classical industrial engineering and MRP, of course, completely missed. So here's some examples of the pull system concept. So this is basically the location where you hold the inventory. So each of these lanes, you're holding a certain item. So there's a customer process. They've received an order for a particular product, so they go to the supermarket, okay, against the authorization to pull a certain item in a certain quantity, and they bring it to the work area and they start processing that inventory. Now, because some empty spots were created in the supermarket, that becomes a signal. It creates a pull. So if this is withdrawal, this is the production signal. So this work center looks at these empty locations, and against the authorization to fill these empty locations, they schedule the production of just those units which were consumed, and they put that back into the supermarket. So that's the whole idea of the Kanban and capping inventory. But notice that the Kanban concept applies between every pair of consecutive work centers in the value stream. Other experts have come about who've kind of modified the fundamental principle of pull. So take constant work in process. Constant work in process says that once you ship something, you kind of release a pull to raw material. Okay, so it's at the raw material end. Now, drum buffer rope, the theory of constraints gurus, their take is you find the bottleneck, the beat of the system, hold a certain amount of inventory in front of it, and as assembly consumes work at the drum, and the drum pulls inventory out of the inventory lanes, appropriately then you send a pull signal, almost like constant work in process, for raw materials to be released. And so as long as the non-constrained work centers replenish what was consumed, that's pretty much how the theory of constraints drum buffer rope pull applies. So again, in a true job shop, the pull concept would simply be you take a set of orders, you sort them by due date, you do a simulated or what is called a soft release of those orders into the system. The finite capacity scheduling system will tell you which orders can be processed and which orders will end up in queue at certain constraint work centers. Then you make a decision whether or not to allow some of those orders to be released if you know that they will end up in queue at the constraint work centers. So again, I'm a big fan of finite capacity scheduling and for job shops, and I don't believe that any of these much touted systems correctly capture the nuances of the job shop. And finally, the fifth step in the lean thinking process, achievement of perfection. And this is again this is more relevant to the CEOs, the VPs, the buzzword today is lean leadership or lean CEO. But I agree, I think when you look at Taiichi Ono, he had considerable executive authority, and because he had that fundamental confidence that what he was doing was right, and because he has the guts to pursue the achievement of what he thought was right, he produced what is now history. It's just historical. The system that he created and how Toyota essentially inspired the entire world, the manufacturing service world, to rethink how they go about doing business, how they treat employees, how they treat suppliers. It's just mind-boggling. So the achievement of perfection is when leadership has a vision of perfection. So they know what the customer values, what products to make, at what cost to quote, how much lead time to quote, how to have continuous improvement programs in-house. I think the best leaders, and I see them at Honda especially, is of course Honda and Toyota out as good, is the leaders came up from the ranks, and so they know the work that now they see their subordinates doing. And when you lead with that level of knowledge, that's the best leadership. Unfortunately, in America, there are too many MBA leaders, and if you aren't an industrial engineer, if you're not really doing things inside the facility, and if your whole approach or view is, economics and marketing and sales, it's a little hard to pursue this vision of perfection. Okay. What's more important is, once you recognize what the market wants, that you also know how to treat your employees, how to measure them, how to inspire them to improve the work they do, and then all the fundamentals of the production system: setup, production, scheduling, material requirements planning, production control, ergonomics, preventive maintenance, plant layout. Just open up an industrial engineering handbook, and that's what you'll see, that all the subsystems have to be shooting on all cylinders. And I think Lean essentially teaches us to rethink the industrial engineering operations management methods and tools that we use to make the production system operate efficiently and effectively. This is also very important. If you read Kobayashi's book, 20 Keys to Workplace Improvement, he's a big fan that a visual, clean workplace is the first step. I kind of disagree. I feel that can be done as part of overarching goals like lead time reduction, but that's fine. I firmly believe that the more that people can see what the market wants, the more that people can see their own performance, the more that people can see quality issues, improvement projects in place, schedules posted or electronically displayed. I think it's important that people have to learn to see the waste. That's how a company achieves perfection. Every employee comes to work saying, how can I squeeze waste out of what I do? How can I help my colleagues who I support, who support me, get their work done faster, better, cheaper? And many times, making waste visible, like the principle of the Kanban square. If you see the red exposed, that means that inventory has really run low. If you see the green spot in the work in process lane filled with a box, you know that there is enough inventory in the queue. So, make waste visible and evident. And of course, quantify it. And finally, develop and implement and sustain a continuous improvement, problem-solving discipline and spirit. This whole lean thinking, it applies to any work, anywhere. Whether you're launching the space shuttle, blowing up somebody, or just feeding food to your newborn child. Or sometimes, like in my case, trying to make an omelette for my children before they go to camp. Everything which we do, there's a process, there's a system. And materials have to be ready, tools have to be ready, instructions have to be ready, equipment has to be ready, people have to be ready. You have to orchestrate them, and the way to do that is to teach everybody problem solving and to instill in them a spirit and attitude. Doesn't matter that you have big improvements, as long as you get small improvements, as long as that attitude. Keep on thinking about how you can improve the work. Keep on thinking how you can help other people do their work. That is so fundamental to the achievement of perfection. So the last bullet I will repeat. You achieve perfection when you develop, implement, and sustain a continuous improvement, problem-solving discipline and spirit throughout the company. Thereby, if you're a service company, you achieve lean service. If you're a manufacturing company, you achieve lean manufacturing. I think lean thinking is a very powerful thought process, but as always, it's hats off to the Toyota production system. They have the best industrial engineers in the world working there. Now, as far as the organization for lean manufacturing, I think every company should try and do it their own way. You have too many consultants coming in with a cookie cutter concept, too many experts writing books as if it's their own. I think that the company has to have people, especially leaders, who understand this. Hopefully people who came from other companies where they learned and practiced this skill. But I think the culture of the company has to be accounted for. You can't get too radical, but there has to be every company's own approach, Secondly, create this attitude that the customer comes first. And it's not just words. It's like, what can I do in the work that I do? How can I improve that? How can I make it waste-free, flexible, error-free, in such a way that I know it will deliver a service or a product to the customer and make them come back to my company for more of the same. And of course, you want to organize the systems and departments of the company into focus factories. So basically what they're saying is, when you create value stream maps, you are taking a product or a service and cutting across all the functional silos that the typical factory, the typical org chart, the typical service company consists of, and I think that's a fundamental limitation of even the hospitals we have. Let's face it, all our factories in America were organized on the principle of function, process, department. We know that is obsolete. We know that when Toyota came around, we started talking about focus factories, we started talking about point of use, we started talking about manufacturing cells, multi-product assembly cells, right? Well, what value stream maps essentially are doing is the same thing. They're cutting across functional silos. So it is important to recognize that it's not just enough to physically organize the manufacturing facility. We need to take that above the manufacturing floor, into the offices, into the org charts, the organization structure, into the leadership of the company. There's a reason why Toyota talks about, value stream managers. It's like there are certain individuals who manage the design of the product, the complete life cycle. There are certain individuals who are in charge of the entire product's network of value streams. So until we say, hey, even our corporate architectures are really based on the obsolete functional / departmental model, unless we organize into cells, teams, focus factories, I think it will be hard for the organization to really get beyond the itty-bitty low-level continuous improvement like Kaizen improvements. Some concepts, practices and techniques, you'll probably have come across these, but you'll see this so-called Toyota house. So this is about the quality. This is about continuous improvement, documented work. I don't know, again, in a high mix environment if Hygienka or mixed model production will apply, but in assembly, it works beautifully. So this is the one pillar, just in time. There's the second pillar, automation, which is human-friendly equipment, error-free. So that means the equipment stops if a defective product is being produced. The equipment stops if a certain amount of inventory has been produced. Of late, I've started seeing a third pillar, and people say that is Six Sigma. I don't know. I think Six Sigma essentially is over here. Again, it's so entrenched in industry, Lean, Six Sigma, TOC, that I might sound like a heretic by saying, Six Sigma is kind of like the foundation of the Toyota production system. Six Sigma is taken for granted when you do Lean or TOC. So this is production control scheduling, continuous flow, produce to attack time, manage inventory through pull, and this is about processes, automation, and of course the goals remain the same. Okay. This is a rather busy slide, but if you look across it, I see all the important components of any production system. But of course, Toyota is the pioneer for that. And all these red circles which you see again, you'll see that in a later presentation on Job Shop Lean. What I'm saying again is that, these components of the Toyota production system just may not belong in a job shop environment. But in a typical production system, again, if you get this book by John Nicholas, especially if you're an academic or a student, I think he does a wonderful job of discussing all these important essential components of the Toyota production system. And if you see again here, this is where perfection is pursued through people empowerment and through strong leadership. The manager is the teacher. So again, I just want to put in a slide that, what's the relationship between Lean and Six Sigma? Like I said before, I think that Six Sigma is already kind of captured in these components of the Toyota production system. If you read Shigeru Shingo's Quality at Source, Zero Defects book, he kind of points out that don't get too taken up with statistical data analysis. Focus on the people, the equipment, the methods, and the materials, the classic Ishikawa diagram components. And he feels that so much of the process and product design and people's training is important to ensure good quality, and not that you can put analysis and inspection to get quality of the product. But still, I believe Six Sigma, but just being an industrial engineer, I think Six Sigma is needed. So is theory of constraints, so is Lean. But again, industrial engineering, if I were to draw a pyramid, if this was TOC, if this was Lean, if this was Six Sigma, I'd kind of put them as the base of the tripod, and this would be industrial engineering. I just think that we need to get beyond that, and that the Toyota production system really is a clarion call to the industrial engineering community to kind of rethink what they teach and do. Once again, in the Toyota production system, where I see Six Sigma naturally contained,